With the capacitive and resistive Romer-Lewin rings, I was able to use this ammeter as a clamp ammeter to measure the current. Unfortunately, uh, with the inductive ring, I need to run at 4 kilohertz, and this instrument is not capable of measuring current at that frequency. It just doesn't have the bandwidth. It just works at 50 and 60 hertz. I need to insert something in the ring to measure the current, and that would be an ordinary ammeter, or, as we will see, this little 1 ohm resistor that will add just a little bit of voltage drop, not that small, but considering the phases, it will not alter the other voltages in the ring, and I will be able to measure the current as a voltage drop across this 1 ohm resistor. The other thing we need to consider is that the total impedance of the ring is about 10 ohms. So the impedance, the internal resistance of the voltmeter, of the ammeter, when inserted in the ring, will change the voltages and will alter the measures. Okay, now I'm trying to measure the current in the ring, and it should be about 9 milliamps. But what I'm measuring with UT61E is just 6.3 milliamps. This is because of the burden voltage on this milliamp range of the instruments. We will change this one to the amp range and see if we get something closer to 9 milliamps. The UT61E is not capable of measuring the current, the circuit. To understand the effect of the burden voltage, we can see that in the ideal ring with no parasitic resistance, both voltages are in phase with each other and the EMF, while the current is 90 degrees out of phase. It is in quadrature and it is lagging by 90 degrees. When we introduce the parasitic resistances, we get a slight change in the phases of the voltages. One is has its phase increased, the other one has its phase decreased. So we move from 85.0 to 84.3 with a degree of with 1.8 degrees, and we change from 17.5 to 18.4 with a phase of minus 8.5 degrees. It has to be this way. One has to tilt in one way and the other has to tilt in the opposite way. The current is no longer 90 degrees in out of phase, but it's just a little bit less. It's 75.6 degrees. When we introduce the 1 ohm sensing resistance that we will see later, we will change the circuit just by a little bit. The 9.6 millivolts that drop across this resistance will lead to just a small adjustment of the voltage values. We can see we are now 82 millivolts instead of 80. No, wait, what was it? Instead of 84.3 and 17.9 instead of 18.5 in terms of amplitudes. The phases are just changed a little bit. What changed a lot is introducing the ammeter with 10 ohm resistance, which is comparable to the 16.45 ohm global resistance impedance of the ring. So it's no surprise that the Argand diagram changes a lot. This is V meter is the burden voltage. This is what is disturbing the measurement, and this is what causes the current to has this very different value, 6.23 milliamps, and a phase lag of just 37.4 degrees. The simulation shows this, and what I want to see is what I measured is 6.25, 6.23, 6.26. So exactly what was expected. I also need to introduce 1 ohm resistor to measure the current. This is it. I already set the voltmeter, measure resistance as a difference. And let's see what we get. Well, I think that's close enough. 1 ohm. That's perfect. Let's introduce it in the ring. And here we go. High-tech device for attaching the resistor. 1 ohm. I would expect about 10 milliamps, 9, 10 milliamps to flow in the ring. I've set the voltmeter to measure AC on the millivolt scale. And let's see what we get. Well, fan my brow. Exactly what we expected. 10.14 millivolts across a 1 ohm resistance. This is 10.1 milliamps RMS in the ring. Considering that the 1 ohm resistor is changing the circuit a bit, we have the confirmation that the theory is right. 10.10, that's it. Okay, now I want to check that the 1 ohm sensing resistor is not changing the voltages across the inductor, or rather along the branches of the circuit. From here to the midpoint here, I'm reading 81 point something, 0.1, 0.07, yeah, 81.1 millivolts RMS. Now if I move this here, I go get, come on, the same point, midpoint there, it's 18 point, okay, 18.4 millivolts. This is the same voltage we should read here, 18.1 millivolts. Let's see, right across the inductor. I should use clips. This is so awkward. .81 millivolts. Of course, the sensing resistor is giving us the current. That is, let's change, 9.8 millivolt. It was 10 when measured here. Let's see. Okay, 9.86, 9.8. That's more or less the current we should measure. And this is just a comparison between the 1 ohm sensing resistor that does not disturb the circuit that much and the ammeter, the UT61E 10.5 ohm internal resistance that changes the current by almost 40%.